When we looked at the limit laws before, there was one limit law in particular, that'd be law number 6, where there was a potential problem. This was the limit law that said the limit as x approaches a of f of x divided by g of x equaled the limit of f of x divided by the limit of g of x, provided two things. First, that both of these limits exist, but also that the limit as x approached a of g of x did not equal 0, so that way you weren't dividing by 0 here. But what happens when the limit as x approaches a of g of x does equal 0? Well, there's two cases to look at. First, we're going to look at what happens if the limit as x approaches a of f of x does not equal 0, and then what happens when the limit as x approaches a of f of x does equal 0. So first we'll look at case 1. So I have law 6 up here in the corner, and then I have case 1. This was the case where f of x, this is the numerator up here, the limit as x approaches a of f of x does not equal 0. So an example of this might be the limit as x approaches negative 3 of x divided by x plus 3. So in this case, we can look at the limit of the top part here. So this would be the limit as x approaches negative 3 of x, and that equals negative 3, so that definitely does not equal 0. And then the limit as x approaches negative 3 of the bottom, that would be equal to 0, which we have for this condition here. So we say we can use this limit law when the limit of the denominator here does not equal 0, but in this case it does equal 0. So what do you do? Well, let's look at a graph of this function. If we were to graph this, we'd get something like this, and we're looking at as x approaches negative 3. And you can see there's a problem here. There's going to be a vertical asymptote right at negative 3, and since there's a vertical asymptote, it looks like as we approach from the left, it kind of shoots off to positive infinity, and as we approach from the right, it shoots off to negative infinity. And so this is a problem. We can just say that overall, since this does appear to be a bit of an issue, this whole limit does not exist. So that's the best that we can say right now. Now later on we'll talk a little bit more about what happens when you have functions like this with asymptotes and how things don't exist. But for now, when we have this kind of situation, we'll just say that this limit does not exist. Now what about case 2? Case 2 is when the limit as x approaches a of f of x does equal 0. So now, and when we have this fraction here, both the numerator and the denominator equal 0. So an example of this might be something like the limit as x approaches 1 of x squared plus 3x minus 4 divided by x minus 1. And so if we were to look at the top, the numerator here, the limit as x approaches 1 of x squared plus 3x minus 4, well, this is just a simple polynomial here. We can use the limit laws to evaluate this. And so we would get 1 squared plus 3 times 1 is 3, so this would be 4 minus 4. This is indeed 0. And we also have, for the denominator, the limit as x approaches 1 of x minus 1, that also equals 0. Okay. So we do have a 0 over 0 situation, and we actually call this the indeterminate form of the type 0 over 0. So it's indeterminate in the sense that we're going to see that it's possible that this still might exist, this limit. We're going to look at an example where it does and an example where it doesn't. So that's the sense in which it's indeterminate. And then of the type 0 over 0, well, we have a 0 on the top and then a 0 on the bottom here. Later on, we'll look at other types of indeterminate forms, but for now, the only one you need to be concerned with is the 0 over 0 type. So one thing you might notice is that this top part factors. So x squared plus 3x minus 4, if we try to factor this, we realize that we get something that is nice. We have a minus 1 here. That's going to end up canceling in the denominator. So we have a minus 1 and a plus 4. Let's just check that. Negative 1 plus 4, that's positive 3, so that's that. And negative 1 times 4 is negative 4, so this works. So I can rewrite this limit now, the limit as x approaches 1 of x squared plus 3x minus 4 divided by x minus 1 as the limit as x approaches 1 of the factored form x minus 1, x plus 4 up top, and we still have an x minus 1 downstairs. So now we're only concerned about what happens as x gets close to 1, but not when x equals 1. The limit doesn't care what happens when x equals 1. So as far as the limit is concerned, this is the same thing as the limit of x plus 4. So these, in a sense, cancel out for the limit here. And when we get that, just x plus 4, well, it's 5. That's an easy limit to evaluate. If we were to look at a graph of this, this looks like a straight line, but we have an open circle here at 1. Why is that? Well, remember, in the original function, when you plug in 1, you're dividing by 0. So we have an open circle here. Notice that this thing right here, x squared plus 3x minus 4 divided by x minus 1, does not equal x plus 4. They're different when x happens to be equal to 1. But in the limit, we're okay, because the limit doesn't care about what happens right at 1. It just cares about what happens as you approach 1. And we can see that as we approach 1 on the x-axis, we approach 5 on the y-axis. Okay, so we just saw a situation where we had an indeterminate form of 0 over 0, and the limit did in fact exist. But that's not always the case. That's why it's called an indeterminate form. Consider this, the limit as x approaches negative 2 of 4x plus 8 divided by x squared plus 4x plus 4. So again, we can look at the top and the bottom here, and we see that we have the limit as x approaches negative 2 of 4x plus 8, and this is easy to evaluate here. This would be negative 2 times 4 is negative 8, negative 8 plus 8 is 0. And how about the bottom, as x approaches negative 2 of x squared plus 4x plus 4, and if we plug in negative 2 here, negative 2 squared is 4, plus 4 times negative 2 is negative 8, so we have a 4, we have another 4, and then we have a negative 8, that's 0. So this, once again, is an indeterminate form of the type 0 over 0. Now, when you have a situation like this, you should always see if there's some way to get an answer. So let's try factoring again. So 4x plus 8 divided by x squared plus 4x plus 4 does factor. We have a common factor of 4 up top, so that gives us an x plus 2. And on the bottom, I think we have an x plus 2 and an x plus 2. Let's check that. 2 plus 2 is 4, 2 times 2 is 4, so yes, this works. So now we can say that this original limit that we had, the limit as x approaches negative 2 of 4x plus 8 divided by x squared plus 4x plus 4 equals the limit of the factored form. So this is the limit as x approaches negative 2 of 4 times x plus 2 divided by x plus 2 times x plus 2. And once again, we have something that cancels. We can cancel out one of the x plus 2 terms. And so this will leave us with the limit as x approaches negative 2 of 4 over x plus 2. But now we have a problem. We're essentially at case 1 now. We have a limit of a numerator here that is not equal to 0, but the limit of the denominator does equal 0. And so this looks a lot like what we saw in case 1. And if we look at a graph of the original function here, we see that indeed as you approach negative 2, we have a problem. There's another vertical asymptote here. And so as we approach from the left, we go down to negative infinity. As we approach from the right, we go off to positive infinity. And so I would say that this limit does not exist. So we see that when you have case 2, an indeterminate form, you need to check, because it's possible that the limit still might exist, but it's also possible that it might not exist.